This is the second kinetic theory lecture. The first one we introduced atomic motion, so we had some atoms bouncing around in a box, and we related their motion to macroscopic properties of a gas like temperature and pressure. So Kelvin decided that the molecular kinetic energy can be related to the Kelvin temperature scale, and when you have 0 Kelvin you have 0 molecular motion and the gas has 0 volume. And when the gas is moving around, bouncing off walls, we related this molecular motion to pressure, and using the Boltzmann constant we related that to temperature using the Kelvin scale. And then we defined specific heats. So these are constants that tell us how much energy we have to transfer to a material to raise its internal energy, so raise its temperature. So if you transfer a heat to a material constant volume, you have a constant volume specific heat, and if you heat a gas at constant pressure, you have a constant pressure specific heat, and the amount of energy that you have to transfer is bigger than what you need to do at constant volume, because the gas also has to do some work, and that energy transferred is called the enthalpy. And we can relate the internal energy and the enthalpy and the work together in what is known as the first law of thermodynamics, and this is our key energy conservation law that we're going to apply in anger when we get to looking at engines, and also when we start looking at flow systems, so when we want to do conservation of energy for flow systems. So this lecture I want to try and introduce why and how our information about what happens in a gas is incomplete, and our problem is our equations don't follow reality. So we observe heat spreading out, we observe milk mixing in a cup of tea, we don't observe a mixed milk in tea unmixing, and we don't observe heat flowing from a cold reservoir to a hot reservoir. And dealing with this is a very difficult issue, because we can't do it in a deterministic way. So we can't do it like we looked at the molecular motion of an atom when it hit the wall. We knew how much momentum that atom had transferred when it had hit the wall. We can only do it in an average sense, and this makes it very difficult to come up with deterministic ways of dealing with this directionality of physics. But it's very important. Entropy change is responsible for all of the inefficiency that we see in engineering. It's responsible for it's the reason that heat engines are only maybe 50-60% efficient and cannot be any more efficient. It's responsible for why we have friction in pipes, why we lose lots and lots of energy when we try and do things to fluids. So what do we know so far? Well, we know we can define a gas using 3 variables. We call these things state variables. So we've got pressure and temperature and volume, which is the extensive form, or we've got specific volume, so that's volume per unit kilo of gas. And these we are going to use when we get on to looking at heat engines, because we can describe how engine efficiency is defined in terms of how these variables change. And we're missing one, and we're going to introduce it in a microscopic way in this lecture, and this missing state variable is entropy. And we've got some universal constants, so these are things that should be constant in our particular universe. Then the Boltzmann constant, so they relate the molecular kinetic energy to temperature, and the universal gas constant, which relates the number of molecules to the macroscopic energy they contain. And then as we're engineers, we're interested in defining changes in masses rather than moles. So we have some mass-based quantities, and these are a function of the material that we're interested in. So we've got the specific heats at constant pressure, at constant volume, got gas constant, and the ratio of the specific heats. And in the previous lecture, we defined Cp and Cv using kinetic theory, but that only applies when our kinetic theory assumptions are valid. So this is only when the only energy that an atom has is kinetic energy, has no vibrational or rotational energy components. So what's the problem? So the problem is that we observe things just going in one direction. So in general, things kind of spread out. So if this thing is heat, heat goes from hot surfaces to cold surfaces, and on average you never see it going in the reverse direction. And if you put a dye in a fluid, in general that dye will spread out, and ultimately your container of fluid will have a uniform colour at some point in the future. And we don't see the reverse happening. We don't observe the reverse happening. And one of the reasons we observe this directionality is it's because there is a change of a property called entropy. So the general sort of directionality is caused by an entropy increase. So things tend to happen in one direction because entropy rises when that happens, and people just don't observe spontaneous things happening in the opposite direction, where the entropy value would decrease. So and this has sort of very much implications for engineering, because we want to define or design efficient machines, and we want to, for instance, with an internal combustion engine, we want to be able to convert a lot of heat energy into work with a high efficiency. And to do that, we have to take into account not only the quantity of energy we have, but the quality of it. So what I mean by that is if we have 1 kilo of material at 1000 Kelvin, and then we have 2 kilos of material at 500 Kelvin, we have the same quantity of energy in these two cases. But if I tried to extract the energy from these two high energy sources, if you like, I would be able to extract more energy from the high temperature source than the lower temperature source. So the higher temperature, smaller mass quantity of energy, from an engineering point of view, has a higher energy quality, because I can extract more of that to turn it into work and make my engine generate some power and my vehicle to move. Okay, so entropy is related to this potential energy quality, and we're going to try and describe it from a molecular point of view today, and in a few lectures time we're going to do it again using the macroscopic way, which is how we do it as engineering. Okay, so this is just a sort of an introductory lecture on what is entropy. Okay, so when we start looking at the temperature of a gas in a box, we look at all of the kinetic energy of all of the molecules, and there's lots of molecules in there, and they're bouncing off each other, and they're bouncing off the walls, and they're bouncing off each other so frequently that when you look at enough particles, you can you can always work out what the distribution of the speeds are. So what we've got here in the figure is on the x-axis, or the horizontal axis, we have the speed of a particle. So if you can imagine, we have a box and we have millions of particles in there, and I managed to pick one out, and it might have a certain speed. So you can imagine that this is the speed axis, and we've got 1, 2, 3, 4, 5 meters per second. Okay, so when we have when the gas has a certain temperature, the probability of the speeds is very well defined. This is called a Boltzmann distribution. So my y-axis here is the probability that a particle might have a certain speed. Okay, so if I have a box and I have millions and millions and millions of particles in the box, and I pick out 1,000 of them, the particle with that I find has the most common speed, if the gas in my box is T1, might be 2 meters a second, say. Okay, and as you go down towards 0, there are less and less particles have this speed, and we have a tail that goes down to here. So there are a few high-speed molecules at a temperature T1. Now, if I increase the temperature of the particles, well, if I increase the temperature of the gas in my box to say T2 or T3, then I change the distribution of speeds of particles in my box. So what happens is, obviously, all of the particles speed up. Well, not all of the most of the particles speed up, and the most probable speed of the particle changes from, say, 2 meters a second to maybe 3 meters a second, and the distribution gets wider. So if you think of these speed intervals as quantized sort of intervals that are fixed regardless of what the temperature of the gas is in the box. The temperature, when the gas in the box is T1, the particle can be have a speed between 0 and 1, 1 and 2, 2 and 3, 3 and 4, and 4 and 5, more or less. And if the temperature of the gas is T2, then the speed of the particle can be 0 to 1, 1 to 2, 2 to 3, 3 to 4, 5 to 6, all the way up to maybe up to 7 meters a second, say. And if you go to higher temperatures, this distribution gets wider and wider and wider. So you might go all the way up to, say, 10 meters a second at this point. So as the temperature gets the temperature of the gas gets wider, there's a wider speed range. It could be, and this is related to how random or how spread out the velocity distribution is in the gas. And this is sort of our first kind of step in trying to understand energy quality in terms of entropy. Okay, so what entropy kind of says is that the more disorder, if you like, or the more spread, the more the information is spread, the higher the entropy is. So these three gases have a different entropy level because the gas molecules have a wider number of possible states. So the gas at T1 has the possibility of being in 5 states. The gas at T2 has the possibility of being in, say, 8 states, and the gas at T3 has the possibility of being in 10 states. And this number of possible states is a measure of the different entropy value of the gas. And theoreticians have tried to come up with equations to define this, and in the same way that you can write a conservation equation for energy. And so Maxwell thought about this, and he decided ultimately that you can't write a deterministic equation. So you can't define the entropy of a single particle. You can only define the entropy of many, many particles averaged over a very, very long time. So he did this thought experiment where he said, right, I've got a box, and I've got a door in the way, and I've got hot molecules, which are the dark ones, and I've got cold molecules, which are the grey ones, and I'm going to put hot and cold gas in the container, and I'll leave the door open for a bit, let them all get mixed up, and then I'll close the door. Okay, so what we've got here in this one at equilibrium is that the temperature on the gas, the average temperature of the hot and the cold things together is some temperature, and the temperature on the other side is the same temperature. So this is what we observe in real life. Yeah. And then he said, well, imagine I could come up with a little sort of fictitious demon, and what he could do is every time a hot molecule came towards the door, he'd open the door and he'd let the hot molecules go through to the container on the right, and if there was a cold molecule on the right hand side, he'd let that flip through into the other one. So what would happen here is that in reality you'd have 2 containers which have the same temperature, and then over a certain amount of time the temperature of the container on the right would get hot, and the container on the left would get cold, and we never observe this in reality, but he couldn't think of any reason why it wouldn't happen on a small scale. So if you can imagine, you have the temperature in a lecture theatre, and there's no reason why small areas of the gas fluctuate in temperature. So they could go up and down due to where these hot and cold molecules might be at any one time. So on a small scale, we can't really work out what's going on, and it's just random. But we can sort of appeal to the big scale, and we can say, well, as long as we average this over a sufficiently long time for enough particles, we observe a directionality in what happens, and we can come up with laws that reflect our observation. This is very much an unsatisfactory way of doing things, because it's not very deterministic. It's not saying, I've got a molecule in a box, and I know if it's going at a certain speed, at a certain velocity, it's going to hit a wall, and it's creating a certain force. So that's a very sort of deterministic, satisfactory way of deriving an equation. Whereas looking at entropy, the only way we can sort of consider entropy is by looking at what lots and lots of particles do over a long enough time. And we can't prove that it's never going to happen. All we can say is we haven't observed it failing yet. So there's another way to think about this, rather in terms of velocity, which is what we did at the start of this lecture. You can think about positional or volume entropy. So this is a nice example of a way to talk about the quality of energy without getting involved in too many equations. So let's consider we have a container and it has a divider down the middle, and on the left hand side there is a gas in there with a certain pressure and a certain temperature, and on the right hand side it's a vacuum, so there's no pressure in there at all, and we're going to assume that this container is rigid, so there's no work going to be done on the gas, and we're going to assume it's perfectly insulated as well, so there's not going to be any heat transfer from the outside in. And we then take the container divider away, and we have to think about what happens. So let's consider the atoms in the container in terms of their molecular kinetic energy. So they had a certain amount of molecular kinetic energy, and we could use the Boltzmann constant to work out what the temperature would be. And when we take the container away, they're just going to carry on moving, aren't they? They're not going to gain in speed or reduce in speed. They're just going to carry on bouncing around the internal surfaces of the container. So the kinetic energy as a whole is not going to change. So the temperature before the divider was released and the temperature after it was released are going to be the same. So T3 and T1 are going to be the same. And the pressure is going to reduce because the pressure is a function of how many times the particles hit the wall per second. So you can imagine if a particle is in a small box, it's going to bounce around a lot and hit the walls quite often. And if the particle volume increases by a factor of 2, then on average the number of collisions per unit time is going to go down by a factor of 2, and therefore the pressure goes down by a factor of 2. Okay, so we've gone from this state to this state, and remember that the gas has done no work, and the gas hasn't had a heat transfer from outside. Okay, so by the first law of thermodynamics, the internal energy hasn't changed. So the energy state in this form and in the large scale form hasn't changed. There's no energy change of the gas. The same energy is there. Okay, and then imagine we wanted to connect a piston up to this face here, and we wanted to make use of that pressure in here to drive a piston to get some work out of it. So it's a sort of super simple engine, if you like. So we're going to get a certain amount of work out of this machine because we've got a certain pressure, P1, and that pressure will make the volume expand, and we'll get some work out of it. So if we connected our same kind of imaginary machine to this container, we're going to get less work out of it, aren't we? Because our initial pressure is now half of what we had before. So this is a nice way of saying, well, we haven't changed the energy content of the gas going from here to here, but the quality of the energy we can extract from it has changed. Okay, so this is a good example of how the energy of the gas has not changed, but our energy quality measure, entropy, has changed. And another way we can define energy is the number of position states. So if you can imagine we have the volume up here and we divide it into 9 subvolumes. So that's what we've got down here. And then we say, well, if I put a molecule into this volume up here, which subvolume is it going to go into? And it has a 1 in 9 probability of going into any one of these things. Yeah. And then when we expand the volume, we keep our quantized volume the same, but instead of having 9 subvolumes, we've now got 18 subvolumes because the volume has doubled. And then if we said, well, if I'm going to put a particle into this second larger volume, what's the probability it will go into any one of these subvolumes? And it becomes 1 in 18. And this change in where might the particle be in space is another way of describing this molecular entropy. So we can define the entropy of a gas using this kind of number of possible states. So remember, this can be one of two things. This can be velocity states or position states. And the equation is the entropy of a particular gas is the Boltzmann constant multiplied by the log of the number of possible states. So this equation on its own is not very useful for us because it really depends on how big we made our quantized volumes. So in the previous example, I said there were 9 volumes that became 18 volumes, but I could have said that there was 1,000 subvolumes that became 2,000 subvolumes, and that would give me a different value for entropy, which is clearly not very useful. But what we can do is we can measure the change in the entropy that's independent of the discretization of our subvolumes or subvelocities. So in our previous example, we said that there were 9 states. So this is the entropy at state 1. That's our initial entropy. And our final entropy is the log of 18 times the Boltzmann constant. So when we work out the change of entropy, so the difference of entropy, so S2 minus S1, which is this delta S, we can work it out, and that becomes 2, it's a mistake, it's not 2 here, so it's KB log 2, and this answer, KB log 2, doesn't depend on the number of states I assumed. So this 2 comes about because the volume has doubled, not because of the number of subvolumes. And we can do the same thing for velocity if we want to. Okay. The other useful reason for using this equation is it gives us a fundamental reference state for gases. So if you remember initially we said 0 Kelvin relates to the case where the molecules are not moving. So if a molecule is not moving, we know 2 things about it with absolute certainty. We know it has 0 velocity, so the number of possible velocity states is 1. And since it's not moving, we know exactly where it is. So the number of possible position states is also 1. So the number of possible states that an atom has, if it's at 0 Kelvin, is 1. And so the entropy of a gas at absolute 0, by definition, is 0. And this is sometimes called the third law of thermodynamics, but it's a nice way of relating the Kelvin temperature scale and the entropy scale in a way that is internally consistent with how molecules move in space. Okay, so we've made a first fairly general stab at trying to introduce entropy from a microscopic point of view. This isn't how we're going to use it in engineering, so to design engines and to look at engine efficiency. We're going to use a slightly different way, but these 2 ways you'll be shown that these 2 things are consistent, and we've ended up defining a third law of thermodynamics. And textbooks, this book, there's one copy in the library, and it's actually a really nice way of trying to understand entropy. It's a short book, and it's very nicely written. And now you can try some chapter 3 questions, try and hand in this one, and I'm going to post this one on Blackboard.